In this module, you will learn about the center of mass of a system of particles. Let us consider a system of n particles with masses m1, m2, mi, mn, and the positions of these particles represented by x1, y1, z1, x2, y2, z2, xi, yi, zi, xn, yn, zn. The center of mass of a given system of n particles is a point in space. If the center of mass C is represented by the coordinates x, y and z, then x is equal to sigma mi xi by sigma mi, which is equal to sigma mi xi by m. Equation 1. Y is equal to sigma mi yi by sigma mi, which is equal to sigma mi yi by m. Equation 2. Z is equal to sigma mi zi by sigma mi, which is equal to sigma mi zi by m. Let this be equation 3, where m is equal to sigma mi is the total mass of the system. The location of the center of a mass of a system of particles depends on the locations of constituent particles and their masses. For example, consider two identical particles, each of mass 2 kg, located at points P of 2, 0, 0 and Q of 8, 0, 0. Since both particles are along the x-axis, even their center of mass lies on the x-axis. X is equal to sigma mi xi by m, equal to m1 x1 plus m2 x2 by m1 plus m2, which is equal to 2 into 2 plus 2 into 8 by 2 plus 2, equal to 5. The location of the center of mass is C1, 5, 0, 0. Note that when masses of both particles are equal, x is a simple average of x1 and x2. What happens to the center of mass if the mass of the second particle is increased to 6 kg? x2 is equal to m1 x1 plus m2 x2 by m1 plus m2, which is equal to 2 into 2 plus 6 into 8 by 2 plus 6, equal to 6.5. The center of mass C2, 6.5, 0, 0, moves closer to the heavier mass. If we place one more particle of mass 4 kg at point R 6.5, 6, 0, where will the center of mass of the three-particle system be positioned? The given set of particles are on the xy plane, and hence the center of mass also lies on the xy plane. On simplification as shown, we get x is equal to 6.5 and y is equal to 2. The position of the center of mass is C3, 6.5, 2, 0. On observing the above cases, we can regard the center of mass of a system of particles as the mass-weighted average location of the constituent particles. In vector notation, the position of the center of mass of a given system of particles is given by R is equal to sigma mi/ri by m, where Ri is equal to xi into I plus yi into j plus zi into k is the position vector of the ith particle, and R is equal to xi plus yj plus zk is the position vector of the center of mass. If we take the center of mass as the origin of our frame of reference, then sigma mi into Ri is equal to 0. Here, the sum is a vector addition. This equation can be split into three equations. Sigma mi xi into I is equal to 0. Sigma mi yi into j is equal to 0. And sigma mi zi into k is equal to 0. In the two-particle example discussed earlier, with masses 2 kg and 6 kg, if the center of mass is chosen as origin, then x1 is equal to minus 4.5 and x2 is equal to 1.5. Sigma mi xi into I is equal to m1 into minus x1 plus m2 into x2, which is equal to 2 into minus 4.5 plus 6 into 1.5, which is equal to 0. When we deal with rigid bodies of continuous distribution of matter, we need to replace the summation symbol sigma in equations 1, 2, and 3 with an integral symbol. The coordinates of the center of mass of a continuous mass distribution is denoted by x is equal to 1 by m integral of x dm. Y is equal to 1 by m integral of y dm. Z is equal to 1 by m integral of z dm, where m is the total mass of the body. The equivalent expression in vector notation is R is equal to 1 by m integral of r dm. We can make use of symmetry considerations while finding the center of mass of homogeneous and regular shaped bodies. For example, let us consider a homogeneous ring of radius r on an xy plane. Let us position the origin at the geometric center of the ring. If we consider a small element of mass dm in one direction, because of reflection symmetry, there is an identical element of mass dm in the opposite direction. If the coordinates of the first element are x, y, then the coordinates of the other element will be minus x, minus y. When all these elements are added, we get integral of x dm is equal to 0 and integral of y dm is equal to 0. This happens only if the center of mass of the ring coincides with its geometric center. Based on similar symmetry considerations, we can prove that the center of mass of a thin rod, uniform disk, uniform sphere, and other such regular bodies lies at their geometric center. You have now reached the end of this module. In this module, you learnt that the center of mass of a system of particles is a point in space whose location depends on the locations of constituent particles and their masses. When the masses of both particles are equal, x1 is a simple average of x1 and x2. We can regard the center of mass of a system of particles as the mass-weighted average location of the constituent particles. We can make use of symmetry considerations while finding the center of mass of homogeneous and regular-shaped bodies. Based on similar symmetry considerations, we can prove that the center of mass of a thin rod, uniform disk, uniform sphere, and other such regular bodies lies at their geometric center.